So the second talk in the session will be about BatchIt, and will be given by Matthew Parkinson.
Thank you. So this is about optimizing message passing allocators that produce consumer workloads. So I'm going to unpack the title because it's quite technical and go through each of the items in there. So I'm one of the authors of snmalloc, which is an allocator some people use, and this is basically some exploration we had in trying to optimize that, thinking about some way in which we could optimize that, which also happens to apply to mimalloc, and this is kind of what we did in that space. So to start with, I'm going to talk about produce consumer workloads. So what do I mean by that in terms of sort of memory management? So here's kind of your... Sorry. Okay, so I hear myself now. Sorry. So what I'm going to talk about is produce consumer workloads. So what do I mean by that? So here's a sort of a simple program where you might have, say, 4 threads. There's one thread being your network ingress, so it's reading from a network, generating work, flowing it through a system. There's a couple of workers that are dealing with the work, and then there's one thread that's putting the work out. So if you think of this from a memory management point of view, your ingress thread allocates some buffer, passes it off to some worker. The worker's going to do some work, possibly generate a response. Some more work comes in on the ingress thread. That gets sent off to another worker. That generates a response. The responses go to the egress thread. All of them sort of, everything's flowing right, and then things start getting deallocated. But what you see is that as you go through this, kind of the blue things are allocated on one thread and deallocated on a different thread. And the yellow things are allocated on one thread and deallocated on another thread. And the orange things are basically what you can end up with is sort of a very asymmetric shape in terms of where something's allocated and where it's deallocated. And often these things are of different sizes, so there isn't kind of a nice affinity to sort of, I can't reuse a response object necessarily as a request object because they might be of different sizes. So you get a flow one way for the application, and the deallocation has to flow in the other direction. So that's what I mean by produce consumer workloads. This is sort of something that you do find in production systems. So what I'm going to focus on next is message passing allocator. So by this, I'm sort of talking about the design of snmalloc, the design of mimalloc, and actually TBB malloc. TBB, Intel's allocator, also has this sort of shape. But before I can kind of go on to that, I want to give you a bit of background on sort of the design of allocators. So for those of you who aren't sort of on the malloc and free side of the fence, this might be helpful. So to start with, in this I'm going to call a single allocation an object, just because that's sort of how I talk, and I can't change that. Size class is an approximation of the size of an object, so we'll just group objects by size classes rather than precise sizes. And I'm going to say slab for a region of memory that contains objects of only a particular size class. Many allocators use a different word. In fact, I'm not sure I found any allocator that uses the same word as another allocator consistently across all the terms. So hopefully this is helpful. So in the beginning, for the design of an allocator, you had a thread, and it was asking for memory. And there would be some kind of data structure indexing the memory, saying what's available, and then there's sort of the chunks of memory. And these could be kind of interleaved in a bit of ways, but basically that's it. There's some indexing structure and some memory. And when you introduce threads, oh, my slide's advanced on its own, you end up with a lock basically protecting this structure. And this is a great point of contention because everyone has to access this every time they're allocating and freeing. So that's not great. So then you get sort of a different design that came out, the one I first came across like this is jemalloc. Horde is similar, but basically you have effectively an allocator per thread. And each of those still has a lock associated to it, so there's some kind of lock to index, so when you're accessing that data structure, but you should have low contention because you're accessing your own allocator, so as long as you're not doing anything like a producer consumer workload, this would be fine. But if you've got anything where you have allocations and deallocations needing to flow between threads, it's not great. So then you get sort of like tcmalloc style, so this is where you have thread caching, so you have one allocator with a lock on it, but then you have some layer of caching on top of it. So in tcmalloc, what might happen is, so for this produce consumer workload, we allocate something from our thread cache. It gets passed across to the other thread. It puts it into its thread cache, but its thread cache is full. So then it goes and grabs the lock and puts it back into the main allocator. Now, depending on how your thread caches are set up, it might go back in individuals, but probably in batches. So it reduces the contention on the lock, but you still have this sort of flowing around the system. And then, obviously, you've emptied your thread cache, so you have to grab the lock to get it back. So in this, you can get some bad behavior. And a project I did quite a few years ago, we were using mimalloc, and we had this producer-consumer style workload, and we kept hitting lock contention because we were batch allocating and batch freeing stuff. And we were just permanently emptying thread caches and basically causing contention. And that was kind of where the design of snmalloc came from, and there's a sort of similar thing in the design of mimalloc, that you want sort of to do some kind of something that doesn't involve locks. So the design of mimalloc, sorry, is Dan here yet? He's not here yet, so I can say it and not worry. He is coming to PLDI, but not this talk, thankfully. So in mimalloc, effectively, for every slab of memory, there's a queue. So when you want to free memory, you put it in a sort of, there's basically a message queue per slab of memory. So if we take our producer-consumer workload, what happens is we allocate some piece of memory from our heap, we pass it off to another thread, and then it sends a message. So it doesn't actually touch the allocator, it just sort of adds it to the queue. So there's a message queue, and then that gets put in there. So this means you're not grabbing locks, you've got sort of lots of queues as well, so there's one per slab. So the likelihood of contention can be quite low, and you're not having to actually do the work of sort of consolidating, working out how many things there are, etc. You're just putting it in a queue, so it's quite a lightweight operation. And, oh, I've missed one animation. Okay, so snmalloc is kind of similar but very different in many regards. So in mimalloc, there was one queue per slab. So one, or actually it's a stack in mimalloc. There's one messaging structure per slab. Whereas in snmalloc, there's one messaging structure per allocator. So every allocator has basically a receive queue and a send queue. So these are all of the allocations, so the send queue are all of the allocations deallocations we need to do to another thread, but we're going to batch them up and send them across in a while. So in this case, when we do our kind of state and produce consumer example, gets sent to another thread, goes into its send, comes in, it goes, oh, this is a not for me, so I'm not going to deal with it directly. And occasionally it checks its receive queue, so it might go, oh, I've got some memory, I better put that back. And then it puts it in its send queue, and then every so often it will send all of those in one batch back to the originating allocator. And there's a bit of a sort of data structure for working out how to do that in kind of batches between different threads, which is in the original snmalloc paper. So that's kind of allocators as I know them. So the final part of the title was optimizing. So to optimize, you have to think of something that's wrong. So in mimalloc, there's really good cache locality when you're doing this because you're sending messages to a slab. So all of the messages are kind of for the same piece of memory, very close together. But every time you send a message, you're doing, in mimalloc, it's a cast loop because it's a stack. So you're doing a serializing operation for every remote free. So every one of these producer-consumer frees. So that's killing your instruction level parallelism. And if you've got contention, it's even worse because you've got a cast loop. So if you happen to be freeing to the same thing from many threads, potentially you've got a lot of things hitting there. So that could be quite bad. And you can sort of create benchmarks that show that for mimalloc. snmalloc, on the other end, doesn't have this issue with the atomic sends because it does all of its batching. It does big batches. It sends them across between threads. It sort of distributes the work. So snmalloc practically does almost no interlocked instructions compared to the amount of allocations and deallocations it does. But it has poor cache locality because everything it gets can be interleaved with other things, so it has to go and read this queue of messages, and they're all over the place. So that then means that, like, when I was when I've been staring at traces of snmalloc, I'll see loads of cache misses on this thing that's supposed to be my nice fast thing, which is not great. So now I can introduce the final bit, BatchIt. So this is basically adding some batching infrastructure into both mimalloc and snmalloc to improve the performance. So in mimalloc, what we're going to have is a little cache, basically, of recently freed things. Now, unlike thread caching, we're not going to reuse them. We're just going to keep them there and then send them in groups back to the originating slab. So this is a slab-indexed associative cache. So I think the one in the paper was 16-way to associativities, but it might have been one associative. 16-way one associative, I think. But we tried quite a lot of different things. So when you get a deallocation in, you put it in the cache. If the cache has some things in it already, if you get contention, just send them across. It's okay. That was what you're going to do anyway in mimalloc. It just happens that if you're doing a lot of stuff to the same slab, you'll send maybe 4 or 5 or 10 deallocations in one go. And that's going to really reduce your contention in the contended cases. Oops. Yeah, so it was that. So in mimalloc, we're doing exactly the same thing. Sorry, in snmalloc, we're doing exactly the same thing as mimalloc. We have a cache now. But what we're going to do is build up these little chunks to go back again. And when we produce our send queue, we're going to make them actually slightly more complicated. So they're going to be, instead of going all over the place, we'll build cyclic lists of the things we're sending back. So we have a list of cyclic lists. So when we send it across, we can process each little cyclic list in one go, and again, that'll have good cache locality, and so basically we get better cache locality as we're going through. And the thing that Wes did that was really nice was he also managed in 16 bytes to store 2 pointers and the length of the list, because obviously you want to keep the length of the list, so then you could add it without even looking at the list, which reduced cache costs even more. So we ran some benchmarking. We did the mimalloc-bench. I'm just going to present a micro benchmark that Wes built that was really nice. So this is kind of like a straight producer consumer, so there's no intermediate workers, just one producer, one consumer. So what we sort of found with mimalloc was that it starts out with a little bit of improvement, and then as you get more ways in which things are going, that's kind of where the contention started to hit in the micro benchmark. So you're getting lots of kind of cost from that contention, so we get to win, and then it starts creeping back this way, which is as you get more and more ways, the likelihood of the cache actually working goes down. So you sort of have this improvement as contention rises, and then reduction as the cache efficiency falls off. Whereas in snmalloc, it behaves very differently. So snmalloc, it basically works really well with the most likelihood of a cache succeeding, because we weren't facing any contention issues in snmalloc. It was all about the cache miss rate. So the better the cache works, the better it works in snmalloc. So it's a slightly different performance characteristic while being effectively the same optimization. So there's further details in the paper. So for mimalloc benchmark results, and both mimalloc and snmalloc have some hardening features, and that also leads to quite a lot of complexity in how you actually implement some of these features when you keep the hardening switched on. So there's graphs and diagrams, and an optimization to mimalloc and snmalloc.
Questions?
Nice talk. Great insights. Just wondering, did you get a chance to look at any bigger workloads? I can see the value in the micro benchmarks in this case, but just wondering if you had any other.
I haven't yet, so that's one of the reasons why we submitted as an intellectual abstract. But we had an idea, and we see how to put it into things, but I need to talk more with Dan to get into mimalloc and look at some benchmarks there. But the use cases for snmalloc at the moment, I'm not sure would exercise this. So
Yeah. Okay. So then the pivot would be, do you have any thoughts on what will happen when you do that? I mean, based on what motivated the work in the beginning?
Sorry, I'm not sure.
Based on what motivated you to go down this path, how do you think this will, can you speculate on how this might perform in the sort of situations you really wanted to work on, as opposed to the...
Yeah, so I think in the real situations we'll have to spend a lot more time looking at cache sizes and associativities and like actually tuning that, because so for a micro benchmark I can find a micro benchmark that hits whatever cache size I want and whatever associativity I want. It's actually finding the right workloads to then stress and get a sort of a good thing, but we've not done that work.
Thanks.
Other questions?
The next speaker doesn't mind having an extra 5 minutes.
I'm trying to pressure the explicit memory management people to ask a question rather than me try to come up with something intelligent. It's not working. Yeah, sort of related to that. Do you think that do you think there are potential cases where it won't perform well that you need to be concerned about?
So for snmalloc, I think it should always be better because it's just doing a little bit of pre-processing. For mimalloc, it's going to hold open slabs of memory for longer, so it can potentially introduce fragmentation. In the benchmarking we looked at, it didn't, because it's quite a small cache. But then the efficiency of the cache might be a problem. So if we make the cache big enough, then we'll hold open more slabs, which then causes more fragmentation. So that's kind of the downside we could see. And with any of these, some of the micro benchmarks in the paper, if it's too small an example, then anything you do to the code change can lead to strange behaviors in terms of performance. Ryan?
This may be kind of a basic misunderstanding of this area, but it seems like both of these strategies, all the strategies you described today, implicitly treat it as the best we can do is to get that freed memory chunk back to the original allocator. But it's a bit frustrating, isn't it? Because you've just touched that memory most recently on the receiver, and you mentioned that there are often differences in size classes that mean that the receiver cannot reuse the memory directly. So do we just kind of give up on that efficiency at the outset and assume the best you can do is get the memory back to the sender? If there are differences in size classes, couldn't we reallocate these chunks or recognize these differences to somehow adapt to this pattern to be able to keep the memory moving forward instead of going back?
Yeah, so when you're doing a size class-based slab allocator, so whenever you're doing a size class-based allocator, it's very hard to change the size of anything because you've sort of committed to that in advance, and there's sort of all your metadata is structured around that, so that becomes a challenge. In the case where it's sort of a similar size, then like the tcmalloc strategy actually works quite well because your thread cache, you can sort of bounce it around nicely in that sense, but even if you've got one thread that's only ever doing deallocation because it's the egress thing, it's just getting stuff in and sending it out and then deallocating, that thread will almost never do any allocation. Right. So you do get some scenarios like this. So I think mimalloc's probably the most widely deployed allocator in this sort of shape, and it does seem to perform very well in comparison to tcmalloc and stuff, even in the cases where you're keeping stuff, even cases that work well for thread caching.
Interesting. So even in an extreme case where we have like 10 or 20 processing stages that are all moving data forward along them, in theory it sounds like there'd be a case where you just switch over to tcmalloc and that might do better at enabling receivers to reuse memory and pass it forward. But in practice, you're saying people just use mimalloc for these examples, and it seems to work better in practice.
I think it depends what company they work for, what they use.
Thank you.
Thank you.